All right, so you can experiment. You can run Sage, verify all that. So let's see why this is true. I'm going to define this function. So I want to write this one down, f1. So we're going to understand this theorem, and this is the setup, right? f1 is z mod p going to z mod p by f of x, x inverse. I define it like this. How about that? Did it look like a function? Not yet, and somebody pointed out why this is not a function yet. So about the z mod p is fp. I think it's finite field. That's where we're going to be forever in this part. Sorry about that. That's right. So here's, I changed to fp, finite field, but you recognize that z mod p is the same as finite field? P elements with a 0 to p minus 1. Okay. So this is not well defined because 0, right? 0 does not have multiplicative inverse. You multiply whatever, you will never get. So we have to define it like this. If this is non-zero, then we're going to define it like this. And if f of 0, then just isolated case. So there we have this function defined, right? Okay. So next thing I want you to do is creating this table. So there's an exercise table. Generate a table for this function f1 defined on 11 elements, finite field 11 to finite field 11. All right? So here's a table. I know you can do this. So I'm going to just write down the answer, and you'll be doing this, f in f1 of x. So here's a 0, 1, 2, 3, 4. Even if you didn't finish the table, I want you to go ahead and fill in the table. Just copy it down. But you got the idea, right? And you're getting this multiplicative, the other numbers. And here, what they're suggesting is that this multiplicative structure, I wrote it down. If I write down 1 and 2 all the way to p minus 1, then in this case, it's going to be all the way up to 10, right? So that's the same as 10 factorial. And we wrote down the relationship such that if you multiply 2 of them, it becomes 1. That's a pretty nice condition, right? In this 1 through 10, they annihilate each other. So can you go ahead and regroup it so that you can clearly see how they cancel each other, right? Does that make sense? Yeah, pair them up. I will pair with 1 is 1, you know that's not much, and 2 and 6, right? I will group in 2 and 6, something like that. All right, you're able to group it. Only the problem is that 1 is there, and 10 is not going to be grouped to 10 itself, right? Because it's only one thing. So from there, these are all 1s, right? They're all 1s. So this is 10. Does it look like a -1 to you in mod 11 world? That was the result. So what is it we have to prove in general case? If I look at this map, in general, in the start part here, f1, map descending to 0 to 0, so that we're not interested in that. 1 through p minus 1, they're all paired up, except that last one, right? What is that, p minus 1? If we can establish this phenomenon in general, then you'll be able to do that, right? So let's look at this table. It's phenomenon. What happened in 10 here? You see what happened in 10? 10 mapped to 10 itself, right? Everything else mapped to something else. So you can pair them up and simply become 1. 10 was the only problem. So if that's, in general, is true. So if f1 of x goes to x itself, x must be what? There are two cases, actually. The very first one, 1, right? Or p minus 1. Is that what we want to conclude? Right. If that's the case, everything else will be paired up with a different element. Therefore, what we just observed in general is true. Okay? So what is this condition then? Let's prove this. That'll kind of do it, right? Does that make sense? Yeah. So prove this. What are we proving? f1x goes to x, then x must be 1 or p minus 1, right? So let's write this one down. Proof. What is f1x? When x is non-zero, I forgot to put. We're not interested in 0, right? So we're only looking at the non-zero element and going to 0 to 0. So let's exclude that case. f1x equal to x is, what was the map again? X inverse, is that right? X inverse is equal to x. That's what we're looking for, right? So how do we turn this one a little bit better? Multiply x both sides. It's like 1 over x. So is that all right if I write it x squared equals 1? Correct? Any questions so far? 1x to the negative 1 is 1 over x squared. So how do you actually solve this equation in real number? Let's see if the arithmetic we have still. You know how to factor this, right? Factor x minus 1x plus 1 equals 0 in finite field. All right, so we conclude in the real number this is going to be 0 or that's going to be 0, and that's the only case, right? Because you understand there's no way two non-real numbers multiplied each other becoming 0. There's no way, right? Therefore, one of the factors must be 0. But how can you conclude something like that in the finite field? Of course, to prove it, you have to pass the modulo p. So let's look at it here. Two quantities are multiplied to each other, becoming 0 mod p. Can I conclude this is 0 mod p or that's a 0 mod p? What is the strong condition that kicks in here, allows us to conclude that? If it is a z mod 6, not z mod p, and you can see 2 times 3 is 0, right? Think about little case of z mod 6 instead of z mod 5. Z mod 5 will be field, right? Z mod 6, here's a 2 times 3. What is it? 0? So 2 is non-zero element in z mod 6, 3 is non-zero element in z mod 6, right? But they multiply, become 0. Can something like that happen in z mod 5? Guess not. And what's the good explanation? Because p is prime number. If it is divisible by p, p must show up here or there, right? What is that big theorem? Unique factorization theorem, right? P must divide something. So either that's 0 or that's 0. Is that correct? That's logic. So from here we conclude, all right, now we understood it must be the case this is 0 or that's 0, right? Because p is prime, must divide either of them. Unique factorization domain property. So that gives you x equals 1. Does it look right? What about the other one? X equals negative 1. It's a different name for that? P minus 1, right? In the finite field. So we conclude that? So from this analysis, what do we know? If you look at this type of table, at the very beginning, 1 goes to 1, right? At the very end, p minus 1 goes to p minus 1. Everything else will be mixed up. So when you look at p minus 1 factorial, only thing that is not matched up is 1 and p minus 1, right? So from there, I'd like to claim that 1 times 2 times all the way to p minus 1 in the finite field, all they're matched up except this first and last guy is not matched up with his own inverse, right? The 2 is matched up 6. That happens. Always different elements, right? Only cases here is that 1 or p minus 1. Everything else is inverse is something else. So they cancel each other. Does that make sense? Good. So that's that. So that proves it, right? That proves it's negative 1, it's congruent to negative 1. That's pretty simple. Can't believe they couldn't figure this one out. But you read about the history, right? But it's always like that. When you have a better proof, it's all clear and easy. That doesn't mean that it's easy to discover. All right. So let me introduce an interesting tweak of this. So why F1? Why did he do that F1? So he's F2, right? F2, FP goes to FP. This is not in the book. Given by f of x. I think about how are we going to generalize this a little bit. It's 2 times x inverse. If x is not 0, and of course if x is 0, we define it just to be 0. Then we're going to do the same game. So we have create a table. In general discussion, not 11 or anything, but I'll show you 11. I create a table here. Why, in the case of F11, so you're not going to go through this calculation. 1 through 3, 4, 5, 6, 2. So I wrote down everything, squeezed in everything. So what do you notice? What is different from earlier table? It's all kind of mixed up, right? All kind of mixed up, but something's different. What is it?
Are we missing 8 in the list of x values?
Yeah, 3 8. So 8 goes to, it is missing 3. So anything that goes there? 8 goes to 3. Sorry about that. 8 goes to 3. 3 goes to 8. I think it's a pair property is still the same. What's different?
1 maps to 2.
Right. The 1 was fixed before, but it's not. So in terms of fixed element, do you see any fixed element here? X goes to x? You don't see any of them, right? You don't see any of them. So let's figure out what happened here. It's any of them. 1 times 2 times dot 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 and p minus 1. If I multiply all of them, right? That's p minus 1 factorial. Now this time we're going to pair up 1 with 2, right? 2 with 1. What are we going to pair up with 3? 8, and A is going to pair up. And you do all that, and the last one is 9 and 10, right? So how many pairs are there? Before there was 4 pairs, because 10 was just by himself, right? This time, I think there's exactly 5 pairs, because none of them are mapped to itself. So 5 pairs? Okay. But what are these all result here? Anybody remember how we got this 3 and 8? X is mapped to, x times y is 2. That's how it's y is 2 times x inverse. Does that make sense? X goes to y, that 2 times x inverse y, that's the same thing as xy become 2. Good? Yeah. So here, this is 2, and that's 2, dot, 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 and you have how many copies of 2? 2 to the 5, right? Isn't that an improvement, you think? Well, 2 to the, well, this is a p minus, well, I'm looking at 11k, so let me go down to 10 here. Right? What does Fermat's theorem says about 11? 2 to the what power is? Two to the 10 is 1. That's Fermat's theorem, right? When p is 11. But here is 2 to the 5 is? Remember what this one did? This is something we already calculated. Wilson's theorem, right? 1 through p minus 1. What is it? Right here, Wilson's theorem. I didn't do anything. It's the same 1 through p minus 1. Slightly different way of looking at it, right? It's negative 1? Negative 1. So not only we know 2 to the 10 is 1. What theorem is that? 2 to the 10 equals 1? Fermat's theorem? Tweaking the Wilson's theorem, what do we know? 2 to the 5th? Negative 1, right? Yes. This type of number that is less than p, such that map is well defined. So, not only we know 2 to the 10 is 1, we know 2 to the 5 is negative 1, right? 2 to the 5 can be 1, anything that's raised to the second power becoming 1 is either plus 1 or minus. We just saw that, right? Yeah. So, if it's 2 to the 10 is 1, then it's 2 to the 5th is either plus 1 or minus 1. It's in the field. But this tells you it's actually minus 1. That's the thing, right? So let's formulate the property that this nice thing happened because it did not repeat. No x mapped to x under F2 map, right? Let's think about this condition, fictitious condition. F of 2 mapped to x itself. Can this ever happen for different prime? It did not happen for 11, did it? According to that table, right? It did not happen. But what is this condition then? What is F2x? 2 times x inverse, right? Is that right? 2 times x inverse. So what is this condition? If I multiply x both sides, do you see that's x squared equals 2? Is that right? It's like 2 divided by x. It's the same thing. How about this one? 2 divided by x equal to x squared equals 2. Is that good? Any question? If there's ever an element in finite field with 11 elements whose square is 2, then there will be a repeat, right? But there was no repeat in here in this table. That means if you square all the elements in 11, there is no 2. 2 is not a square of something in mod 11. Because of that, they go like this, right? Can you imagine maybe 17, 2 is a square? Then this map will repeat exactly. There's one element to repeat. X goes to x, right? And then you do this Wilson's theorem again, and you get some result, but different. Different. What does that be? Different. How is it going to be different from here to there? If it is not -1, it's going to be +1. That's the difference. Right? That's your homework problem. So you're going to do Wilson's theorem, and I'm going to give you some situation like this. What is the, 2 to the p minus 1 over 2? Right? So that's, if you just follow this one, I think it's pretty easy. All right? It's a nice tweak. From there, and you can further, not only I discovered if I square this, what do I get? I get Fermat's theorem back, right? So I can actually prove Fermat's theorem using this. Whether it's a square or not, you will have this type of situation, plus minus 1. If I raise it, I always get 2 to the p minus 1 equal to 1. So it's an alternative proof of Fermat's theorem, right? You will discover that. Good? 9.